Now, you might remember from AS, Kc. Now, Kw is based on the Kc of water dissociation. So I'm going to write down the equation of water dissociation, which looks like this. Now, this equilibrium lies mostly to the left. So if I was to draw an ice table, let's assume initially we had something like 100 moles of water and 0 moles of hydrogen and hydroxide ions. Then the change would be something really small, like -1, and that means you gain 1 proton and gain 1 hydroxide ion. So essentially, your equilibrium moles is 99, 1, and 1, okay? Now, your water, it was 100, and now it's 99, right? And that's quite similar. So essentially, your water has barely changed, okay? Your concentration of the water initially is the same as your concentration of the water at equilibrium, okay? Because it's barely changed. Now, this is really useful afterwards. Also, a good thing to take note of is the fact that the amount of hydrogen ions formed is the same as the amount of hydroxide ions formed. So essentially, your H plus concentration is equal to your OH minus concentration. Alright, now that we know these things, we can derive the formula for Kw. Now the Kc expression for the dissociation of water looks like this. Now we can multiply both sides by H2O concentration, which gets you... Okay, so here we have Kc times the concentration of water, right? Now, from AS, you should know that the value of Kc at a certain temperature is constant. So nothing can affect the value of Kc apart from temperature. Not changing the concentration, not changing the pressure, nothing can change the value of Kc apart from temperature. So therefore, Kc is a constant. Now the concentration of water, we said barely changes because the equilibrium lies mostly to the left. So because it barely changes, you can basically call it a constant as well. So essentially, you have two constants multiplied together. So that just forms another constant. And what we do is we call this constant Kw. And this is how the formula for Kw is derived. Okay, so Kw is the Kc of water dissociation. Kw equals H plus concentration times OH minus concentration. Just like we said before. Remember to write this in square brackets. The value of Kw at room temperature is 1 times 10 to the minus 14. Probably going to get used to seeing this value a lot. Now, if we look back at our ice table, we said that H plus concentration equals OH minus concentration. And we can see that because the number of moles of H plus formed is the same as the number of moles of OH minus formed. Okay, and this is for the dissociation of pure water. Okay, so for pure water, H plus equals OH minus. I'm just going to write down the charges. Okay, and this is the concentration, right? Now, because of this, in our Kw expression, we can substitute the OH minus over here for H plus. So that we get Kw is equal to H plus times H plus, which is basically the same thing as H plus squared. Alright, so I've got a question for us here to try. Calculate the pH of water at 50 degrees Celsius, given that the value of Kw is 5.476 times 10 to the minus 14 at 50 degrees Celsius. Okay, so we know that the Kw is equal to, right? However, at pure water, it's also equal to H plus squared, because OH and H plus is the same. Now we know in this instance, Kw is equal to 5.476 times 10 to the minus 14, so we can sub that into our expression, and we get... Now we can square root this to get the concentration of H plus, which is... And now we can minus log this answer to get pH, and we get 6.63. Now just remember, the main thing to do when you're asked to work out the pH is try and get the H plus concentration at equilibrium. Because from there, all you have to do is minus log the H plus concentration to get pH. Okay, so you also need to know, why does temperature affect Kw? At different temperatures to 25 degrees Celsius, the pH of pure water changes. Le Chatelier's principle can predict the change. The dissociation of water is endothermic. Okay, so I'm just going to write that down. Okay, so that means this side here is endothermic. Okay? So increasing the temperature would push the equilibrium to the right. So if I write down the formula, Kw equals H plus times OH minus. Now, essentially, when we increase the temperature, since the forward reaction is endothermic, the equilibrium shifts to the right, so you get more H plus and more OH minus. Now this means that the product of the two will increase as well, which is the value of Kw. So the value of Kw increases, but the value of H plus, like we said, also increases. Okay, so the value of the hydrogen concentration increases. Now, we know that when the hydrogen concentration increases, the pH gets lower. Okay? Because if you think about the pH scale, this side here is more acidic, and this side here is more alkaline. So as we increase the H plus concentration, the pH will shift to this side. Okay, for your exams, you also need to be able to work out the pH of a strong base. So we've been asked to calculate the pH of the strong base, 0.1 moles per decimeter cubed of sodium hydroxide. Now, since sodium hydroxide is a strong base, it dissociates fully. So this means if we have 0.1 moles per decimeter of sodium hydroxide, we're also going to have 0.1 moles per decimeter of hydroxide ions. Okay? This is because it's a 1-to-1 molar ratio. Now we can sub this into our expression for Kw. So we know that Kw equals H plus times OH minus. Now when Kw isn't given to us, we can just assume it's the value at room temperature, which is 10 to the minus 14. And we know that the concentration of sodium hydroxide and the hydroxide ions is 0.1. Now we can just divide through to work out the value of H plus concentrations, which is... And finally, we can minus log this to get pH. So our value for pH is 13. Now, this seems like a suitable answer, because if you think about the pH scale, we said that it goes from roughly 1 to 14. And, well, if 7's neutral, then a strong base we would expect to be somewhere around here. 13, 14, 12, somewhere around there. So this seems like a good answer to get.